In this video, we are going to cover data cleaning and pre-processing. What are we going to do? We are going to discuss missingness. We are going to refer to what missing values are about, how to diagnose them, and we are going to mention, without getting into much details, because we've already have a video available for that. I will refer to that later. Um, I will discuss a little bit about that, the MCAR, the MAR, and the uh, not missing at random mechanism that we would like to know about so that we know whether we have to impute or not, whether we have to delete, things like that. And then we'll basically learn how we can choose um, uh, imputation methods. There are different types of imputation. We'll talk about that. And then we will talk about outliers. We will discuss different methods how we can detect and also how to treat outliers. And we will refer to transformation and scaling. There are certain things that I'm not going to get into the details because I've already shared another video with you that discusses the definition, so I'll skip certain things. But after the lecture slides, I will get into some practical aspect of all these. So why do we need to clean data? Obviously, there when you have a data set or a database, all right, your fields, there are fields that are going to be obsolete sometime. There are fields that are redundant. There are different reasons. For example, there are missing values, there are outliers. These are the main issues that we might find in a data set, apart from other issues that you might have in a database. For example, there are inconsistent values that are included, unshootable format. For example, in a date column, you have at some point in time you have 12, let's suppose 22 September, like this, 2025. At another point in time, you have something like this. All these are inconsistent in terms, these are not shootable format, rather not inconsistent as well, but unshootable formatting. They are meaning the same thing but with different formats, so we have to adapt and bring everything to a single format. There are inconsistent values as well. There are different issues that might arise in a data set. For example, let's suppose you are talking about salary, and one moment you get somebody, I'm just taking an example like that, writing is get a salary of 20,000, comma, something like that, comma, 0 0. And then at another point in time you get something like that, you get something like 20,000.00. I suppose you got something like that. So we have to be careful because you see, for example, here, these two are the same thing, but sorry, this I need to remove here. So these are the same thing, but they may mean they may be from different how do we say format again. You have, for example, French generally use commas to represent decimal places, whereas in English system it's a dot that representing decimal places. So then what happened if you have, let's suppose these data come from a survey, and there are different countries involved, and each one have written their data, have input their data as they are. And if they input their data as they are, they each one of them use different style of writing. For example, one is writing comma here, one is writing dot here. They mean the same thing, but you need to bring a consistency everywhere. So that's what I mean, is that in a data set you need to ensure that there is consistency. You need to remove any outlier, not remove a, you need to deal with missing values, you need to deal with outliers. All these are different problems that exist in a data set. The idea behind is obviously to minimize gigo. Minimize gigo means is that you want to minimize the garbage in to get minimum garbage out. I will get into quickly the missing data mechanism, but I just want to remind you that we already have a video that I've shared with you. Let me just show you. Sorry, let me just open that and share it with you. So I already have a video that I've shared with you um, in Google Classroom, which is of an overview, all right, of lecture 7. So this video is available on YouTube as well, and you can easily go for it. You will see here I speak about different things. I talk about the concept of missing values. I talk about data cleaning. I give some example. I talk what is data imputation. So that's why I'm not going to repeat these different things that I've mentioned already. So you can go through the video. The video is available in the link on. It's available in Google Classroom. All right. So the video is available on Google Classroom, as you see. So you can go through that. It already discusses many of the things that I'm going to mention. That's why I'm not going to take too long on this video to introduce this concept. So you have a missing data mechanism, and you have, for example, the missing completely at random mechanism, which is MCAR. And here we refer to missingness being independent of data. And in fact, this is the kind of missing mechanism that we would like to rather have, missing completely at random. All right, we would like to have this kind of missing mechanism. If this missing mechanism exists, then we can, for example, apply a listwise deletion, as we refer to as a complete case is the same thing as a listwise deletion. You may delete the data as far as there are not many, obviously. And there are also the missing at random, which is in fact missing conditionally at random. We also refer to that as missing conditionally at random if we want. Um, when we look at the MAR, it is missing at random, but the term is missing at random, but it is in fact missing conditionally at random rather. And this missing conditionally at random it means that your missingness depends on observed variables. All right. So your missingness depends on observed variables. I would kindly ask you to refer to the video for more description on that, obviously. And then you have a not missing at random. So for the missing at random, you can still deal with it through a model-based imputation method, or where you can use a regression model and so on just to be able to impute these data. That's not a problem as well. But when it comes to the not missing at random mechanism, this is the worst case scenario. You do not want to have this not missing at random mechanism. This not missing at random mechanism is a worst situation. We don't want that. Because the missing not missing at random means that your data depends the missingness depends on the day variable itself. The missingness depend on the variable itself. If, for example, salary is missing, you will see that, let's suppose, all people with highest salary are not available. And if all highest salary are not available, it means that there is a problem where this variable itself is producing the missingness pattern. In other words, it is not a good thing. So then you will need to decide, impute what to do with that kind of variable, especially if this is your target variable. It becomes a big problem. So you need to decide what to do, but imputation is not recommended in such case. If there is not missing at random, it's rather advised not to impute. Maybe you need to improve the quality of the data, get more data or whatever, but you can't impute. That's one thing. It's not appropriate to impute. Now, when we talk about missing diagnostics, When I'm referring to all these different things here, how would you know whether you have to impute or not, for example? To know whether to impute, you would like to know whether your data is not missing at random, for example. Even, or you would rather know if the data is missing completely at random, rather. Donc, to be able to do that, you can apply the Little's MCAR test. The Little's MCAR test that I'm going to discuss later on for a practical session. The Little MCAR test will be able to give you, it tests the hypothesis that your data is missing completely at random or not. So if your data is not missing completely at random, it's advisable not to not to apply imputation. If your data is missing completely at random, farewell, you can apply your imputation. That's not a problem. You can also compare means or plot observed versus missing by group or time. What does this mean? It's like, let's suppose you have different variables. You have variable x and you have variable y. Okay, you have other variables as well. Let's suppose you have 2, 3, 7, or whatever, and then you have a missing here. You have missing, you have 4, and then you are missing 7, 5, for example, different values. And then you have x here, x which could be anything. Let's suppose it is 2, 3, 1, 5, and 7, things like that. And then you have 4, 8, and then you have 4, things like this. What this principle tells you is that you can just compare the mean across missing and not missing. So you create another column that will be called flag. Let's suppose I call it flag. That will say whether the data is missing or not. For example, here this is missing, you call it 1. And here it's 0, this is 1, 1, this is 0. So you have a set of missingness. You have two groups here, one which are missing, one which is not missing. So you just need to compare the mean with respect to those values which are not missing, and with regard, then you compare it with all these values which are missing. Basically, that's what it is. You have to compare with all those values which are missing. Here you find the values of x and compare. If they are different, that would indicate if the average of x when the data is missing and the average of x when the data is not missing are different. That would probably indicate that the data is not missing completely at random. You can also do box plot, things like that, to verify that, to see if the distribution has changed a lot or not. So if the data has changed, there is probably the data is probably isn't the missingness isn't random. It's not missing completely at random, so it isn't necessarily random. If the value, if the average or the distribution based on the box plot is not the same, that's the kind of thing that you can do using the Little's MCAR test, and also compare the means or box plot, things like that. And then you also have you can also check the percentage of missingness. That's also important. You need to be able to check the percentage of missingness. If, let's suppose, most of the data that I have are missing, everything was missing, I've got only let's suppose 10% of data, and 90% is missing for a particular column, for example, then we have a problem here. Probably we will not be using that column at all. We will not be using that variable at all if there is such a high percentage of missing values. So it's a bit subjective here. It depends a little bit on what you believe is a high percentage or not. So, but it's not only about the high percentage, it's also about if the data is not missing completely, it's not missing at random as well. We can't just look at the percentage. That's also important. Then we can look at the impute. We can look at the imputation options that we have. And the imputation option that we have numeric imputations that can be done through mean or median. If your data is quantitative, when you have decided, okay, the Little MCAR test mentioned that the data is missing completely at random, then you may decide to impute. And when you decide to impute, there are different options as you see here. You have the mean, median. You can also find median by season or months, things like that, if the data is time series, for example. You have the the LOCF, which means last observation carried forward. Uh, there is l- when you have a missingness for the previous time point. Let's suppose you have a data like this, you have a data like that, and then you reach January, and then you see that there is no data for February, and then you need to go to March. Let's suppose this is a monthly data. You have something like that. The tourism arrival, let's suppose for February, is not available. The last data that you have is for January here, but you don't have that of February, but you have as from March onwards. There's a missingness here. So what you do then? You take the last observation and you carry it forward. This last observation is what you have here, so you just take it as it is here and we move on. So we just replace this missingness by the last observation. That's the principle of um, last observation carried forward. But you also have other methods like we call linear interpolation to predict this value that is missing. These are different things that exist. When the data is categorical, you won't be able to use a mean or median, obviously. But if your example there is gender, you don't know the gender of somebody, you can impute that gender based on the mode, for example. Or if you still don't want to impute it, and you can create a new class called unknown as well. And then there is one thing that is important to understand is that it is important that you do not impute the target. I've mentioned target here as an example, but it is advisable never to impute the target. This is just why I've been referring to why as a target, but this is not the best thing to do to impute a target. Why? Imputing a target is generally not recommended because it can introduce what we call bias in your model. It can introduce even significant bias. Remember that the target is what you are predicting, is what your model is predicting. And if you are filling in, if like in this example, if y is the target, if you are filling in missing values for it, you are essentially providing the model with the answers that it should be learning to find on its own. So you are teaching the model things that it should be able to do on its own. You are somehow influencing the model by imputing values here. Let's suppose if you impute the mean, you are basically influencing all this data towards the mean, and it's not a good thing. Whatever method that you are using, it's not necessarily the best thing to do. It should be avoided because you are introducing bias, because it is basically what you are modeling. If there are missing values in your features, that's okay, you can, there's no problem as such. But if, if your target variable is itself having missing, it is advised not to how do we say, not to impute the target. Basically, why? Because you are introducing bias in your modeling. And the issue here is that it is, let's suppose if you have a huge percent, not a huge, let's suppose 10% of the data is missing in Y. It's not good because it's quite a lot. Let's suppose you have only, maybe let's suppose you have 1% of data. 1% also is a lot. Let's suppose you have 0.1% is missing. Maybe you can allow yourself to impute, but it's still not a good idea. It's advisable not to impute. So what do you do then? If this is the case, then it's probably better to remove the probably better to remove the rows or the cases where you have a missing. That's basically what is better to do, so that you do not introduce fictitious value that might bring bias, not might, that will automatically bring bias in your model, that will significantly bias this model that you are going to apply. So maybe it's better to delete. But of course, again, whatever I'm saying is based on the assumption that the data is missing completely at random. If it is missing conditionally at random, that's a different story. All right. Or if it is not missing completely at random, that's a different story as well. It's not even advisable to delete. If it is not missing at random, it is not even advisable not to delete. All right, not deleting. So basically, it's not of quality. So you need to find out a way of getting more information with regards to these missing values, maybe. Now, then we have outliers. Okay, uh, outliers. There are outliers which are genuine extreme, and there are outliers which are data error. Obviously, there are outliers which are part of pattern, and there are outliers which are genuinely extreme values, and also um, part of it, an error. For example, let's suppose in salary, most people, suppose you have a salary column, most people are getting around, let's suppose, 10,000 in those digits, okay, 5 digit values. And then all of a sudden, only one person get something like, let's suppose, 200,000. Now, it may be a genuine extreme value, that's for sure, but it can also be a mistake. It could happen that somebody has added a zero by mistake in the imputation, in the input process. So we then need to identify why this is like that. If this is just part of genuine pattern, then there is transformation that can be applied. But if it is an error, then you correct the error, obviously. Okay, and then you have influence. You have to understand that outliers normally should be dealt with as because it influence your data, it influence your model, in because basically it's just influence the mean. You know that means are affected by outliers. If you calculate a mean of 2, 4, and 6, just calculate the mean, and then just replace the 6 by 400, calculate that mean, and then you keep other values like that: 3, 1, 3, 2, 5, things like that. Most of the data are around these values. So if you look at these values, you could say that the average would be 3. But just because of one single value, which is an outlier like that, that average of 3 will be distorted completely and you will get a very big value. So normally outliers affect your mean, even affect your ordinary least squares method, affect many other models, and it is good that we deal with them. And how do you detect these outliers to be able to deal with them? These are the rules. I mentioned that in the video. I'm not going to take too long on that. But you can use the interquartile range rule where you look at the lower fence. This is referred to as the lower fence, by the way. This is referred to as the lower fence, and this is referred to as the upper fence. So you can see if a value goes below the lower fence, then it is treated as an outlier. If a value goes above the upper fence, it is treated as an outlier as well. What is Q1? What is IQR? And so on. Q1 means the lower quartile. This is what we refer to as the lower quartile. Q3 means the upper quartile. And IQR means upper quartile minus lower quartile. That is what we refer to as the interquartile range. So any value that goes below this lower fence, that is this value that you have computed, is going to be considered as an outlier. And any value that goes beyond this value here of Q3 plus 1.5 times IQR will be considered as an as an outlier again. Then there is another method that is available to check if your data contains outlier is through standardization. You standardize your data. That is what is meant by standardizing your data. You just need to take the value of x that you have, you subtract the mean, you divide by the standard deviation. You take your value of x, you subtract the mean, and you divide by the standard deviation. That is what we refer to as standardization. So standardization allows you to know when you apply this formula of standardization, you are able to know if a value of z is going to be greater than 3 or less than negative 3. If a value is less than negative 3 or is greater than 3, you can say that it is going to be considered as an outlier. Of course, this assumes that the data is roughly normal. But the problem arises is that when you are using the z-score method, you will see that it is based on the mean. And when it is based on the mean, you would recall I just mentioned earlier that outlier is already affected by the mean. So you are using a method that uses the mean to be able to detect an outlier which is affected by the mean. So this is um, okay as long as the data is roughly normal. But if the data is skewed a lot, it is not advisable to use this score, because some values will be wrongly detected as outliers and other values will be detected as outliers as normal, but some values will be wrongly detected as outliers when they are not necessarily outliers sometimes. So that's one of the issue that you have with the z-score. I'm not going to get into that too much. And then you have the other method that we call the robust. I'm going to mention that later on, the robust method. What is it? We'll refer to that later on. And then we have the outlier. How do we treat that? We can treat an outlier in different ways. Number one, we need to verify the source, as you would have remembered. If it is a data error, you remove the error, you clear the error, you fix it. And then, if an outlier is part of the pattern of a data and it is a genuine outlier, you might decide to winsorize the data, where you put a cap on the values that you have. Then you also have the option of transformation, where log transformation is usually used when you have to deal with um, outliers. That's a very common approach of using the log transformation. You can also use square root transformation. All these are different methods that you can use for treating outliers. Then there is, when we talk about the different transforms that I've just mentioned here, like log, square root, etc. When do you apply these? It depends. If your data is right skewed, positive, then you may apply log. Obviously, I'm not talking about negative because there are negative values, and log here would not be necessarily helpful. But when you have, for example, things like that, a data that is right skewed, you can apply log transformation that will help in removing the outliers, will transform the data. Then you have, when you're dealing with count data, now, count data, you can apply square root of the count. Generally, that's one of the method that is appropriate. I'm not getting into the details here, but I'm just mentioning it. You have, when you have heteroscedastic residuals, especially when you apply OLS, for example, and if your data does not abide by the assumptions of OLS of homoscedasticity, then you may apply a log transformation as well on your response or your predictors, and that is also a possibility to apply transformation. All right. Now, we also have the concept of scaling, and here we have transform, you have the scaling. So we also have a transform. We have the scaling. You have different scaling that can be applied. I mentioned to you earlier the z-score is a scaling method. All right, and you take the mean, you subtract, you take the value, you subtract the mean, and then you divide by the standard deviation. That is generally used in PCA. You use that in generalized least squares, generalized linear model. Excuse me. You'll use that in generalized linear model. Then you have a min-max normalization, where all the values of your data are going to lie between 0 and 1. Basically, what is done in min-max normalization is this. Sorry. You take your value of x, you subtract the minimum value of x, you divide by the maximum value of x, subtract the minimum value of x. Maximum value of x minus the minimum value of x. So what is min-max normalization? It is taking your value of x that you have. If you have, let's suppose, 1, 2, and 3, you will take, for example, you have to normalize these. You will take x, which is your first value here. You subtract the minimum, which is 0 itself. You divide by 3 minus 1, that is 2. So if you take 1 minus 1, you get 0. Divide by whatever it is 0. Now, if you take the last one, the value of x as 3. So 3 minus the minimum, which is 1. So 3 minus 1, divide by what is the maximum of the value of x, which is itself 3, minus the minimum, which is equal to 1. So you get 1 here. And what about the other value of x2? So you basically take 2 minus the minimum, which is 1, and you divide by the maximum, 3 minus the minimum, 1. So in other words, you get 1 out of 2, which is 0.5. So that's what it is. So in the end, when you apply min-max normalization, you bring all of your values in between 0 and 1. So I was mentioning the robust method earlier. So the robust method is basically here. Uh, when you're talking about robust, you are talking about taking your x, subtracting the median. You take your x, you subtract the median, and you divide by the interquartile range. The advantage with that is especially when you have very strong outliers in the data. If you have a data which contains, which is outlier heavy, I can say it like that, then it is preferable to apply the robust method. If a data does not contain that much of outliers, that's okay. There's not much of a problem. But if the data contains quite a number of outliers, it is good to apply the robust method, because the median is not affected by outliers, neither is the interquartile range. Both of these methods are fine normally when you have to deal with heavy data, um, heavy outliers. It is important to understand that there is a difference between scaling and transform. All right. When we talk about transformation, we are not talking necessarily the same thing as scaling. Transformation will normally change the shape of your variable. You see, if you apply log transformation on a data that is right skewed like this, that data will look probably like a normal distribution, maybe. All right. So it reduces the skewness, it stabilizes the variance. You have log, you have a root transformation, you have other methods that I'm not mentioning here. For example, there is Box-Cox transformation, there is Box-Cox transformation, and others as well. And then you have remember that when we are talking about transformation, we are talking about a change in the shape of a variable distribution. So basically, when we talk about transformation, transforms normally will tackle distributional issues like skewness, heteroscedasticity, nonlinearity. All these are the things that transforms look at. On the other hand, when we are dealing with scaling, uh, normally scaling will generally change the units or magnitude so that the variables are comparable. That's the idea. It will change the unit or magnitude so that the variables are comparable. So normally it will bring, for example, everything on the same center, or in the context of min-max normalization, all the variables, irrespective of what they were before, will be lying between 0 and 1. So then it makes things a little bit easier to compare. These things like min-max normalization are absolutely essential when you apply different methods, like, for example, neural network, for example. You can't do a neural network without applying min-max normalization. This is very important. So scaling will normally tackles comparability, all right, in distance, excuse me, in distance. You have methods that uses scaling is like k-means, for example, that you will learn later on. There are different methods, like you have ridge regression and so on, that uses scaling. So scaling, what it does is that it preserves the shape and correlations. uh, it won't normally turn a curve relationship into a straight one. like in this one here, you will see that a data that is like this will be changed to, for example, if a data, maybe not like this, let's suppose you have a data that is like that. All right, if your data is like that, like y and x, and you start applying log transformation, when you apply log transformation on your data, that same data that looked curved like this will become linear. All right, it will become linear. So it changes the shape of a distribution completely in terms of right skewed to something normal, and then you can see here what's going on. But when you talk about scaling, that is not necessarily the case. In scaling, it preserves the shape, but it won't necessarily turn a curved relationship into a straight one like this. Okay, but when you apply log transformation, you get something like this. If you take the log of y with respect to x, that is what is going to happen. That changes to this. You can give it a try on Excel yourself and play with some values. You will see that this is going to happen if you take the log. When I talk about log, it depends. You can talk about log to base 10. You can talk about log to natural log. Most of the time, we will refer to natural log, that is ln. When I'm referring to log, it means that I'm referring to ln generally. Irrespective of how I write it as log. Generally refer to it as ln. It's referring to ln normally. So that's one thing. So remember that scaling here does not, scaling on its own will not fix skewness or heavy tails. All right, it will not fix skewness or heavy tails, but Z score can even amplify outlier influence, as I mentioned to you. So you have to be careful with that because it is based on the mean itself. So what, to sum up, what we want to do in this um, lecture today. I've just given you an overview of what we are doing and what are these different methods. We'll get into the practical aspect of all these in a moment. So what we want to do is that we want to import our files. Then when we import our data in R, we are going to have a profiling of the data. What does it mean by that? It means that's where I'm going to check my data, what's going on in the data, whether there are missing values, what is the percentage of missing values, what is the distribution, and so on. Excuse me. Then I will clean the data based on what I've seen in the profile, and then I will apply the model. But of course, we're not going to do the modeling here in the class, but this is a workflow generally of what you do. You import your data, you profile your data, you clean. When I say you profile your data, you check if for outliers, how much outlier you have, what is the percentage of missing, you verify if it is MCA, all these kinds of things, and then you do your appropriate cleaning. If the data is MCA, you can apply deletion methods, but you can also apply imputation. So you clean, and then you are going to apply your model after having cleaned the data. So that's the kind of workflow that we deal with when you have to pre-process the data, okay, to apply a model. And then you create a log as well. Generally, I'm mentioning that creating a log, especially for your assignment purpose, sometimes when you are doing something, it's good that you create a log that is an accountability record. When I talk about log, I'm not talking about log transformation, please. I'm referring to log, which is a logbook, for example, where you write down all the details of what you have done, especially in terms of the cleaning process, what you have observed, what you have done. You write it down, and you mention all the different changes that you brought in the data, and you script it, and you ensure that it is reproducible, so that somebody else can look at it, somebody else can apply the same cleaning and get the same result like you. So that's the kind of things that we want to do. Okay, though I'm not going to get into the details of modeling and the creating of log, I will generally refer to the importing. I will basically do only the importing, profile, and cleaning in this class. Okay, because it's only a 1 week lecture. I don't want to get into all these details right now. The next part of the video now would be to do some practical analysis in R, applying, for example, these different concepts that we have learned, like apply the little MCAR test to see if the data is missing completely at random, etc., etc. So that's our next step now.